conductor ampacity for an intermittent duty elevator motor is determined by the time rating of the motor because the motor's ability to cool itself depends on the time it is running. Let's consider a 5-minute rated motor. This motor is designed to operate for short periods, for example 5 minutes, at its rated horsepower. During this time, the motor generates heat that is dissipated through its frame and winding insulation. The conductors are sized at 85% of the motor nameplate current to ensure that the heat generated during these intermittent operating periods does not cause the conductors to overheat. Now let's examine a continuous rated motor. This motor is designed to operate continuously at its rated horsepower. As such, it generates more heat over time than a 5-minute rated motor. To ensure that the conductors do not overheat, they must be sized at 140% of the motor nameplate current. This provides sufficient ampacity to handle the increased heat generated by continuous operation. To summarize, the time rating of the elevator motor is used to determine the conductor size because it influences the amount of heat generated by the motor and, therefore, the ampacity required to prevent overheating of the conductors. The key factor is heat. Motors, when running, generate heat. The amount of heat generated and how well the motor can dissipate that heat determines the required conductor size. A motor designed for short bursts of operation, a 5-minute rated motor, can tolerate a smaller conductor size as the heat build-up is less significant. However, a motor designed for continuous operation generates significantly more heat and requires larger conductors to handle the continuous current and prevent overheating. The code requirements in Table 430.22e are there to ensure that the conductors are adequately sized to handle the heat generated by the motor under different operating conditions. Understanding the rationale behind these requirements is crucial for ensuring the safe and reliable operation of elevator systems. Let's explore this further. Imagine two identical motors, both rated at the same horsepower and operating under the same load conditions. However, one motor is designed for intermittent duty with a 5-minute rating, while the other is designed for continuous duty. During operation, both motors draw the same amount of current to perform the same amount of work. However, the continuous duty motor will generate more heat over time due to its sustained operation. This increased heat can cause the conductors connected to the motor to overheat if they are not adequately sized. Overheating conductors can lead to insulation breakdown, short circuits, and even fires. Therefore, the NEC requires that the conductors for a continuous duty motor be sized larger than those for an intermittent duty motor to prevent overheating and ensure the safety of the electrical system. The percentage factors in Table 430.22e, such as 85% for 5-minute rated motors and 140% for continuous rated motors, are based on empirical data and engineering calculations that take into account the heat-generating characteristics of different types of motors. These factors provide a safety margin to ensure that the conductors can handle the worst-case operating conditions without exceeding their temperature rating. It's also important to consider the ambient temperature and the type of insulation used on the conductors when determining the appropriate conductor size. Higher ambient temperatures and lower rated insulation types may require even larger conductors to prevent overheating. In addition to the conductor ampacity requirements in Table 430.22e, other factors may also influence the overall conductor size. These factors include voltage drop, which can reduce the motor's performance, and fault current carrying capacity, which ensures that the conductors can safely withstand short-circuit currents. Therefore, it's essential to consult all applicable codes and standards and perform a comprehensive engineering analysis to determine the appropriate conductor size for each specific application. Finally, keep in mind that proper installation practices are just as important as selecting the correct conductor size. Ensure that all connections are tight and secure, and that the conductors are properly supported and protected from physical damage. Regular inspection and maintenance can also help to identify potential problems before they lead to equipment failure or safety hazards. By understanding the principles behind conductor sizing for elevator motors and following all applicable codes and standards can ensure the safe and reliable operation of these critical systems. Let's consider NEC Article 430 in more detail. NEC Article 430 provides comprehensive requirements for the installation and protection of motors, motor circuits, and motor control equipment. It covers various aspects of motor installations, including conductor sizing, overload protection, short-circuit protection, and grounding. Within Article 430, Section 430.22 specifically addresses the sizing of conductors supplying motors. This section provides detailed guidelines for determining the minimum ampacity of conductors based on the motor's nameplate current rating, duty cycle, and other factors. As previously mentioned, Table 430.22e is particularly relevant to the sizing of conductors for elevator motors. This table provides adjustment factors for different types of intermittent duty motors, such as those used in elevators and cranes. The adjustment factors in Table 430.22e account for the fact that intermittent duty motors do not operate continuously at their rated load. Instead, they operate in cycles of starting, running, and stopping. This allows the conductors to cool down during the off cycle, which reduces the overall heat build-up. Therefore, the conductors can be sized smaller than they would be for a continuous duty motor with the same nameplate current rating. However, it's important to note that the adjustment factors in Table 430.22e are based on certain assumptions about the motor's duty cycle. If the motor operates more frequently or for longer periods than assumed, the conductors may need to be sized larger to prevent overheating. In addition to Table 430.22e, other sections of Article 430 may also be relevant to the sizing of conductors for elevator motors. For example, Section 430.24 provides requirements for sizing conductors supplying multiple motors. This section may apply if the elevator system includes multiple motors, such as those used to drive the car and the doors. Section 430.52 addresses the sizing of short-circuit and ground fault protective devices for motor circuits. These devices are designed to protect the conductors and equipment from damage in the event of a short circuit or ground fault. The size of the protective devices must be coordinated with the ampacity of the conductors to ensure that they will trip quickly enough to prevent damage. When sizing conductors for elevator motors, it's also important to consider the voltage drop in the conductors. Voltage drop occurs when the voltage at the motor terminals is lower than the voltage at the source due to the resistance of the conductors. Excessive voltage drop can reduce the motor's performance and efficiency. Therefore, the conductors should be sized large enough to minimize voltage drop to acceptable levels. The NEC provides guidelines for calculating voltage drop in conductors. These guidelines take into account the conductor length, ampacity, and operating temperature. In general, the voltage drop should not exceed 3% for power circuits and 5% for lighting circuits. In addition to the NEC requirements, other codes and standards may also apply to the installation of elevator motors and conductors. These include local building codes, elevator safety codes, and industry standards. It's important to consult all applicable codes and standards to ensure that the installation meets all requirements. Furthermore, it's essential to use qualified and experienced electricians to perform the installation work. Electricians who are familiar with the NEC and other relevant codes and standards will be able to ensure that the installation is safe and compliant. They will also be able to identify and address any potential problems before they lead to equipment failure or safety hazards. In summary, the sizing of conductors for elevator motors is a complex process that requires careful consideration of various factors, including the motor's nameplate current rating, duty cycle, ambient temperature, and voltage drop. The NEC provides detailed guidelines for sizing conductors to ensure that they are adequately protected against overheating and other hazards. By following these guidelines and consulting all applicable codes and standards can ensure the safe and reliable operation of elevator systems. The time rating of a motor refers to the length of time that the motor can operate at its rated horsepower without exceeding its temperature limits. Motors are typically designed with either a continuous time rating or a short time rating. A continuous rated motor is designed to operate continuously at its rated horsepower without exceeding its temperature limits. These motors are typically used in applications where the load is constant and the motor is required to operate for extended periods. A short time-rated motor is designed to operate at its rated horsepower for a limited time period, typically 5, 15, 30, or 60 minutes. These motors are typically used in applications where the load is intermittent and the motor is not required to operate continuously. The time rating of a motor is an important factor to consider when sizing conductors. Conductors must be sized to carry the motor's full load current without exceeding their temperature limits. The NEC provides specific requirements for sizing conductors based on the motor's time rating. For continuous rated motors, the conductors must be sized to carry at least 125% of the motor's full load current. This is to account for the fact that the motor will be operating continuously and generating heat. For short time rated motors, the conductors can be sized smaller than for continuous rated motors. The NEC allows the conductors to be sized based on the motor's duty cycle. The duty cycle is the percentage of time that the motor is operating at its rated load. For example, a motor that operates at its rated load for 5 minutes out of every 15 minutes has a duty cycle of 33%. The NEC provides tables that specify the minimum conductor size for different duty cycles. In general, the conductors for short time rated motors can be sized smaller than for continuous rated motors because the motor is not operating continuously and generating heat. However, it is important to carefully consider the motor's duty cycle and to ensure that the conductors are adequately sized to carry the motor's full load current without exceeding the temperature limits. In addition to the motor's time rating and duty cycle, other factors that must be considered when sizing conductors include the ambient temperature, the type of insulation used in the conductors, and the length of the conductors. High ambient temperatures can reduce the ampacity of conductors. The ampacity of a conductor is the amount of current that it can carry without exceeding its temperature limits. The NEC provides tables that specify the ampacity of conductors based on the ambient temperature and the type of insulation used. The length of the conductors can also affect their ampacity. Longer conductors have more resistance, which can cause the conductors to heat up more. The NEC provides formulas for calculating the voltage drop in conductors. Voltage drop is the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can reduce the performance of the motor. Therefore, it is important to size the conductors large enough to minimize voltage drop. In summary, the sizing of conductors for motors is a complex process that requires careful consideration of various factors. The NEC provides detailed requirements for sizing conductors based on the motor's time rating, duty cycle, ambient temperature, type of insulation, and length of the conductors. By following these requirements, it is possible to ensure that the conductors are adequately sized to carry the motor's full load current without exceeding their temperature limits. This will help to prevent overheating, voltage drop, and other problems that can reduce the performance and reliability of the motor. Let's delve deeper into the concept of motor cooling and its relationship to conductor sizing. The ability of a motor to dissipate heat is a critical factor in determining the appropriate conductor size. Motors generate heat due to several factors, including electrical resistance in the windings, friction in the bearings, and core losses in the stator and rotor. This heat must be effectively removed from the motor to prevent the temperature of the windings and other components from exceeding their insulation rating. If the temperature exceeds the insulation rating, the insulation can break down, leading to short circuits and motor failure. The rate at which a motor generates heat is proportional to the square of the current flowing through the windings. This means that even a small increase in current can lead to a significant increase in heat generation. Therefore, it is essential to ensure that the conductors supplying the motor are adequately sized to carry the full load current without causing excessive heat build-up. The rate at which a motor dissipates heat depends on several factors, including the motor's design, size, and cooling method. Some motors are designed with built-in fans that circulate air over the windings to remove heat. Others are cooled by liquid, such as oil or water. The effectiveness of the cooling system depends on the motor's environment. Motors operating in hot or poorly ventilated environments will dissipate heat less effectively than motors operating in cool or well-ventilated environments. The time rating of a motor is directly related to its ability to dissipate heat. A continuous rated motor is designed to dissipate heat continuously at its rated load. This means that the motor can operate at its rated load indefinitely without exceeding its temperature limits. A short time rated motor is designed to dissipate heat only for a limited time period. This means that the motor can operate at its rated load for the specified time period, but it must be allowed to cool down before being operated again. The NEC takes into account the motor's time rating when specifying the minimum conductor size. For continuous rated motors, the conductors must be sized to carry at least 125% of the motor's full load current. This is to ensure that the conductors can handle the continuous heat generated by the motor. For short time rated motors, the conductors can be sized smaller than for continuous rated motors. The NEC allows the conductors to be sized based on the motor's duty cycle. The duty cycle is the percentage of time that the motor is operating at its rated load. This allows the conductors to cool down during the off-cycle, which reduces the overall heat build-up. Let's consider the specific case of elevator motors. Elevator motors are typically used in intermittent duty applications. This means that the motors operate for short periods of time to lift and load the elevator car, and then they remain idle for longer periods of time. The duty cycle of an elevator motor depends on the building's height, the number of floors served by the elevator, and the frequency of use. In buildings with high traffic, the elevator motors may operate more frequently and for longer periods of time. In buildings with low traffic, the elevator motors may operate less frequently and for shorter periods of time. The NEC recognizes that elevator motors are used in intermittent duty applications. Therefore, the NEC allows the conductors supplying elevator motors to be sized based on the motor's duty cycle. Table 430.22e provides adjustment factors for sizing conductors supplying intermittent duty motors. These adjustment factors take into account the motor's duty cycle and the length of time that the motor is allowed to cool down. By using the adjustment factors in Table 430.22e, it is possible to size the conductors supplying elevator motors to provide adequate protection against overheating without oversizing the conductors. In addition to the motor's time rating and duty cycle, other factors that must be considered when sizing conductors for elevator motors include the ambient temperature, the type of insulation used on the conductors, and the length of the conductors. High ambient temperatures can reduce the ampacity of conductors. Therefore, it is important to consider the ambient temperature when sizing conductors for elevator motors. The type of insulation used on the conductors also affects their ampacity. Conductors with higher temperature insulation ratings can carry more current than conductors with lower temperature insulation ratings. Therefore, it is important to select conductors with the appropriate insulation rating for the application. The length of the conductors can also affect their ampacity. Longer conductors have more resistance, which can cause the conductors to heat up more. Therefore, it is important to size the conductors large enough to minimize voltage drop and prevent overheating. In summary, the sizing of conductors for elevator motors is a complex process that requires careful consideration of various factors. The NEC provides detailed requirements for sizing conductors based on the motor's time rating, duty cycle, ambient temperature, type of insulation, and length of the conductors. By following these requirements, it is possible to ensure that the conductors are adequately sized to carry the motor's full load current without exceeding their temperature limits. This will help to prevent overheating, voltage drop, and other problems that can reduce the performance and reliability of the elevator system. It is essential to consult the latest edition of the NEC and other applicable codes and standards when sizing conductors for elevator motors.